Hi guys, I'm Lisa, your online calc tutor, and today we're going to talk about the definition of derivative. Now before we jump into some examples, I would like to just kind of motivate the definition a little bit, just to get a sense of why this formula is important or how it comes about. So basically, if you've got a function, what are we trying to do when we calculate a derivative? We're trying to find the slope of the tangent line to our function at a certain point. So if this value here is x, what we're going to do is, what we're really interested in is finding the slope of the tangent line to this curve, the line that's tangent at the point x. So if I were to draw that in, something like this, so we're going to say that the slope of this tangent line is equal to the derivative at the point x. That's what we're trying to calculate. But how do we do something like that? We know how to find the slope of a line if we know 2 points on the line. Here we only know the 1 point. So what we're going to do is choose a nearby point. So I'm going to choose this point, which we're going to think of as x plus h. So h is like a small number, right? So we're like a small distance away. And the idea is that we want the slope of the green line, but we're going to kind of get at it by finding the slope of this pink line, which passes through the curve at the point x, comma f of x, and at the point x plus h, comma f of x plus h. Right, just to kind of fill that in a little bit, I'll just go over here, right? The y coordinate of this point is going to be f of x, and the y coordinate of this point going to be f of x plus h. So the slope of the pink line, so that slope is going to equal change in y over change in x, which the change in y is going to be f of x plus h minus f of x. And the change in x, well, x plus h minus x, and that's just h. So that's the slope of the pink line. But we really want the slope of the green line. So how are we going to do that? We're going to take the x plus h point and let it approach x. How do we do that? You do that by taking a limit. So f prime of x, that slope of that green line, I'm going to get to it by taking the slope of the pink line, but letting h approach 0 in that formula. So that's the idea. That's where this definition comes from. Okay, so that's the definition of derivative. Now, let's actually see it in action. Let's use this definition to find the derivative of functions that we know. So let's find f prime of x using this definition for the function f of x equals x squared. So we'll use the definition. Okay, so we're going to go limit h approaches 0 so I'll just recopy the definition here. And okay, so let's just write over here. So so now for f of x plus h, once you have a specific function in mind, how do we find f of x plus h? Well, we just replace x in the definition of the function with x plus h. So instead of being x squared, I'm just going to replace the x with x plus h, and that gets squared. So that's f of x plus h. And then we have f of x, well, that's just x squared. and this is h, and we're taking the limit as h approaches 0. So now we're just going to use our knowledge of limits. We're going to use techniques of evaluating limits to simplify this and get an answer. So I'm going to expand the x plus h quantity squared. So that's just multiplying a binomial using FOIL. So if we do that, we'll end up with x squared plus 2xh plus h squared. And then we still have the minus x squared over h. Okay, and now I can see that these x squared terms in the numerator are going to cancel out. So we'll get rid of those. And now we can observe that every term in this expression has h in it. So I'm going to go ahead and factor out h from the top. And now you can see there's an h as a factor in the numerator and an h in the denominator, and those are going to cancel out. So we're going to be left with just limit as h approaches 0 of 2x plus h. And now we're almost done with this limit. We can just we've basically resolved the indeterminate form by canceling that common factor of h. So now we can simply replace h with 0. We can substitute 0 in for h, and that's going to give us 2x. Okay, so we successfully used the definition of derivative to find the derivative of the function x squared. So I'll just summarize that here. So f of x is x squared, and we found using the definition of derivative that its derivative is equal to 2x. So what does that really mean? That means that this derivative formula is giving us a formula for the slope of the tangent line to the function x squared for any point x. So maybe just to illustrate that quickly here, why don't we draw in the function x squared? Okay, let me try and draw this a little bit accurately so that we can see that this formula is actually, it really works. Okay, so I'm going to graph the original function f of x equals x squared. So of course that's a parabola whose vertex is the origin, and it passes through the points 1, 1, 2, 4, negative 1, 1, and negative 2, 4. So let's actually choose specific values of x in this derivative formula here. So if I let x equal 1, so when x equals 1, then we have that f prime of 1 equals, I'm just going to use the derivative formula we calculated, 2 times 1, or 2. So what that's saying is that if we draw in the tangent line to the curve at the point when x equals 1, so at this point 1, 1, so what the derivative told us is that the slope of that line should be 2. And that looks quite plausible, right? So this green line that I drew certainly looks like it could have a slope of 2. That's what the derivative formula is telling us. It's telling us that if you choose a specific value of x, you go to that point on your function, the tangent line will have that slope at that value. Let's try it for another value. Let's try when x equals negative 2. So when x equals negative 2, again, I'm just going to use the derivative formula we calculated, 2x, so f prime of negative 2 is going to equal 2 times negative 2, or negative 4. Okay, let's just summarize that the slope was 2. F prime of 1 equals 2. Okay, let's do the same for this value here. So when x equals negative 2, I'll also go ahead and draw in the tangent line there. Okay, so what the derivative tells us is that the slope of this line is -4. F prime and -2 equals -4. So that's what the derivative is telling you, this derivative formula. It's saying that whatever value of x you choose, if you go to that location on your original function, the function x squared, you draw in a tangent line at that point, the slope of the tangent line is going to be given by the value you get when you plug in that x value into the derivative formula. Okay, let's do another example. Let's try, okay, let's do f of x is equal to 1 over x. Okay, so I'm going to, again, rewrite that definition of derivative. Okay, now let's apply this definition to this particular function, f of x equals 1 over x. So I'll just repeat that definition, substituting in that specific function. So f of x plus h, again, we take the formula for f of x and replace every instance of x that we see, we replace it with x plus h. So in this case, that's going to give us 1 over x plus h, and then subtract f of x. So I just use the formula and then over h like so. Okay. So in this case, we have fractions within a bigger fraction. So what I'm going to do to make this a little more manageable to work with is I'm going to rewrite this a little bit. So we have this expression on the top divided by h. So whenever we divide by something, we can also think of it as multiplying by 1 over that quantity. So here we're dividing by h. So I'm going to kind of rewrite that and consider that we are multiplying by 1 over h rather than dividing by h. So I've got 1 over h times the numerator. Okay, now I'm going to, we're going to want to basically combine these two fractions inside the parentheses there into a single fraction by finding a common denominator. So the common denominator in this case is going to be the product of these two denominators, because they don't have any common factors to them, so the common denominator will just be their product. So for the 1 over x plus h fraction, I'm going to multiply top and bottom of that by x, because that will give me the common denominator in the bottom. Right? That'll give me the x plus h in the bottom. And then for the other fraction, the minus 1 over x, I'm going to multiply top and bottom of that fraction by x plus h. So I'm going to have x plus h over x plus h. Okay. So now we can combine this into a single fraction. So the denominators are the same, so we can simply subtract the numerators. So we have x. I'm going to just go ahead and distribute the negative sign. We have x minus quantity, x plus h. So that'll give us x minus h in the numerator, and in the denominator, x plus h. And now you can see that we're going to have, the numerator is going to simplify. We have x minus x there, so we're just going to be left with a negative h up top. So we have negative h over, and I'm going to just go ahead and also just kind of multiply these two fractions, right? So we have 1 over h times this fraction. So the 1 can multiply on the top, that won't change anything, and the h can just multiply with what's on the bottom. So we're just left with a single fraction that looks like this, and you can see there's a common factor in the numerator and denominator of h, and we can cancel that out. So we'll be left with limit h goes to 0 of negative 1 over x times x plus h. And again, we've resolved the indeterminate form of this limit by canceling those h's. So now we're at the final stage. We can simply replace h with 0 in this formula now, and so our limit is going to evaluate to negative 1 over x times x, or negative 1 over x squared. Yeah, okay. So great. So we found that our original function was f of x equals 1 over x, and our derivative function using the definition is negative 1 over x squared. Okay, why don't we do a final example? Let's do f of x is equal to mx plus b. Okay, so this is a little more of a general example, but it'll give us a nice general result that we'll be using all the time when we're doing calculus, right? So m and b here are these are constants here. So this is a linear function, right? This is a straight line. So we're gonna by applying the definition of derivative to this function, we're going to end up with a formula that'll apply to any function that is in this form. So if you had, f of x equals 2x, or 3x minus 1, or negative 5x plus 3, right? These are all examples of functions of this type. So this is going to give us a kind of more general formula that'll apply to any linear function when we want to take its derivative. So I'll go ahead again and write our definition of derivative. And we can then substitute in the actual function. So f of x plus h, again, I'm going to take every time I see an x in the definition of the function, replace it with x plus h. So in this case, I would have m times x plus h plus b. And then I'm going to subtract the function. So that's just mx plus b. Put it in parentheses because that negative sign will apply to the entire function. We want to make sure we apply the negative sign to the entire thing. So, and then we just need to simplify a bit here. I'll go ahead and distribute the m. So I have mx plus mh plus b, and then I'll distribute this negative sign also. So I have minus mx minus b. That's my numerator, and then still all over h. And now we can see that we're going to have some cancellation in the numerator. Mx cancels with mx, b cancels with negative b, and we're left with a limit as h approaches 0 of mh over h. Of course, mh over h simplifies. We can cancel the h, so we're just left with m. And now we don't have any h's left in our expression, so m is basically a constant. So limit as h goes to 0 of a constant will just be that constant. So what we found, so the result is that if your function is linear, a straight line, mx plus b, so m and b are constants here, then its derivative is just going to be m. And of course, in a standard calculus course, you're going to, be taking the derivative of all kinds of functions quite often, and you'll certainly encounter linear functions constantly. So this result you'll use quite a bit. So I hope you enjoyed this video. I hope this shed some light on how you apply the definition of derivative to find derivatives of various types of functions. If you have any questions or comments, please put those in the comment section. If you have a request for a video that you'd like to see, please let me know that as well. And click that subscribe button, guys. And I hope you have a great rest of your day and you enjoy your study of calculus. Until next time, take care.